This video is going over the paper 3 questions for fluid dynamics. These are recent IB questions, complete with the mark scheme and, where applicable, the examiner's report. And so we'll be going through those solutions. And so the first question is from November 2020, and so it asks what are state two properties of an ideal fluid. We know that ideal fluid properties are incompressible, you can't squeeze it. It's non-viscous. Remember that viscous, if something is viscous, it's thick and syrupy, so we don't want our ideal fluid to be thick and syrupy. We want it to flow like water, so that's non-viscous. And in laminar or streamlined flow, the alternative to laminar flow is turbulent flow. So you don't want the flow to be turbulent. And it wanted two of those three things. Okay, fine. Then it goes on to say, a sphere is dropped into a container of oil, and it says the data are available, gives the density of the oil, gives the viscosity of the oil, it gives the volume of the sphere and the mass of the sphere. And then it says determine the terminal velocity of the sphere. And so we have a sphere that is falling through oil, it's falling downwards, and so friction will oppose motion, so the drag force is going to be the other way, the drag force is going to be upwards. And so we have a drag force going upwards opposing the motion. We have the weight, which is of the sphere, which is pulling down on the sphere, and of course there's the buoyant force of the sphere in the oil. And its terminal velocity, when you have terminal velocity, there's no more acceleration. So if there's no acceleration, the net force is also zero. So we have the drag force is given by the data booklet is 6 pi viscosity radius of the sphere that is falling times the speed times the terminal velocity, which is what we're looking for. And then the buoyant force on the sphere is the density of the fluid it's in times the volume of the displaced fluid, which would be the volume of the sphere, times g, and that's given from the data booklet as well. And then mg, of course, is the weight of that sphere. We don't have radius of the sphere, but we do have volume, and so we can get the radius in terms of the volume. So then our radius would be the cube root of 3 times the volume over 4 pi. And so now we have the expression in terms of all of the things that are defined for the problem. We have the volume that's given, we have the viscosity of oil, we have the density of the oil, we have the mass of the sphere, so the only thing that's missing is the terminal velocity. Looking at the mark scheme, it seems that they decided to go ahead and find the radius of the sphere first and then plug that back into the expression. That's probably simpler in terms of the algebra, but let's solve for v and go from there. In fact, I'm going to put my solution for v right next to that for the mark scheme. So collecting terms and putting v on the left side. I actually didn't collect terms. I probably could have put in parentheses m minus density volume, but let's just proceed from here. As I write down the viscosity, I comment on PAS. What the heck is PAS? That is Pascal seconds. And a Pascal is a measurement of pressure, and the Pascal is a Newton per meter squared. So yeah, let's take a look at that for a second. So yeah, Newton over meter squared times seconds, or Newtons times meters to the negative 2 times seconds. I don't know why they put 37.9 times 10 to the negative 3 instead of 3.79 times 10 to the negative 2, but who's counting? Okay, those are all the numbers. So yes, after all those numbers are all squeezed in, we do in fact come up with the answer from the mark scheme, 6.84 meters per second. Just a tip on this problem, yes, the drag equation has terminal velocity in it, but don't forget that we need to analyze this as the sum of the forces, so we need to include the weight and the buoyant force. Don't forget those suckers as well. So yeah, I would say that A was a lot simpler than B. And then, so the 3 marks from B, one was dealing with either the volume or the radius, figuring that out. And then Once you've processed that, putting the equation together for step 2, for mark 2 rather, and then the correct answer would be mark 3. And it says, like I did a little hand waving on the radius and the volume, it says allow implicit calculation of radius for marking for mark point 1. Do not allow error carried forward if you forget about the buoyant force, like I said, and accept use of g equals 10, which could give you a velocity of 7.0 meters per second. All right, then it says sphere is now suspended from a spring, so the sphere is below the surface of the oil. And so the problem, and that is CI. And so the problem implies that if the spring were not there, then the sphere would fall. I mean, I think that the terminal velocity of B it doesn't actually say the sphere falls, but the fact that you had to solve for a terminal velocity, that there is a terminal velocity, means that the sphere does not float in the oil. That's the point. So since it doesn't float, that means that the buoyant force does not equal the weight, hence the spring. Now, what am I getting at? And you could say this here is at rest, sum of the forces is equal to 0. Now, this is all vertical forces, by the way. Obviously, there's no horizontal forces side to side. But you might say, now, in the previous problem, the sum of the forces was also 0 because of terminal velocity, which means that there's no acceleration. But in that case, the ball was moving, and if it's moving, it experiences a drag force. In this case, since it's at rest, there is no drag force. And so what we have here is that we have mg for the sphere pulling downward. We have the buoyant force opposing, pushing upward because of the pressure. I think that's what, Archimedes' principle? Anyway, from the buoyant force, and then the spring is doing the rest of the vertical holding, taking care of the rest of the upward vertical force. And so once to solve for this, the force of the spring. So again, the mark scheme kind of lays it out nicely. So yeah, we have the force of the spring plus the buoyant force going up minus the weight going down equals 0. Therefore, the force of the spring is the weight minus the buoyant force. We know from the data booklet that buoyant force is density of the fluid times the volume of the fluid displaced times g, hence the mg minus rho vg that it shows there in the mark scheme. And I'm not going to rewrite these numbers when they're already written here in the mark scheme. We have the mass in kilograms of the sphere. We have 9.81, which is g. We have the density, which was given to us before in the problem. We have the volume of the sphere, which is the volume of the liquid displaced, and then we have g again. So we run those numbers through, and we get for a force 5.86 times 10 to the negative 2 newtons. Ta-da! So there you go. All right. And then it says you can use g for 10. If you use g as 10, you wind up with a 2 sig fig answer of 6.0 times 10 to the negative 2 newtons. Okay, fine. CII. And CII says sphere oscillates vertically within the oil at the natural frequency of the sphere spring system. Energy is reduced in each cycle by 10%. So every time it cycles, it's losing energy, and it wants the Q factor for the system. So this is not a B3, this is a B4 thing, and this is making reference to something called damping. So we will be getting to that soon. Let's actually take a look. It's worth discussing, it's worth talking about. And so this Q factor is 2 pi times the ratio of the energy stored to the energy lost. And so if it's losing 10% of its energy every cycle, then that ratio of stored to lost is 100 over 10. And so this Q factor, this damping factor, is 63. Which, again, is like, say what? Yeah, we haven't looked at Q factor yet because we haven't done B4 yet, but we will. It's the very next topic, so it's worth discussing now just for a little tiny bit. C3, outline the effect on Q of changing the oil to one with greater viscosity. And viscosity we know. And so if it's more viscous, it is a thicker fluid. And just think about it. If you think about an oscillating spring going through a thick fluid, say like honey or something like that, you can imagine it's not going to be oscillating for long. The fluid is going to slow down the oscillations. It's going to reduce the amplitude of the oscillations, which we call damping. And so if it's a thicker fluid, that drag force is going to increase because the viscosity, the drag force increases because the viscosity increases. And so if there's a greater drag force, it's going to cause greater energy loss per cycle. So it's also worth discussing C double I a little bit because C triple I actually is a B3 fluid dynamics question. It's really a little bit of both. Anyway, let's move on. I really dig these questions. I like how they tied in viscosity to an oscillating system. Anyway, so now we have number 2, and it's a pitot tube for airspeed. So one of the key principles of the pitot tube is these two tubes here, we're representing A and B, and then tube A is at static atmospheric pressure, and then tube B, so the air is flowing into tube B, but then it's smacking into this wall there, essentially, and so it stops the air at that point, and that's called stagnation pressure, where the pressure there is zero. I'm sorry. Stagnation pressure where the velocity is zero. Pressure is definitely not zero. The pressure is higher than the static atmospheric pressure. And so since the airspeed is zero at the at that wall of the hooked tube, the curved tube at B, I said the speed is zero, right? Then the pressure is going to be higher. We can show that with the Bernoulli principle. That's 1/2 rho speed squared plus rho being density, plus density times g times the difference in height, which there is no difference in height really, so that goes away, plus the pressure equals a constant. And so I can set them equal to each other since that's constant. We get 1/2 rho velocity at a squared plus the pressure at A is equal to 1/2 rho the velocity b squared plus the pressure at B, but that portion goes away because the velocity at B is equal to 0. And so what I'm left with, 1/2 times the density times the speed of the air at A squared plus the pressure at A is equal to the pressure at B, so therefore the pressure at B is greater than the pressure at A. As for the difference in the air column height, that has to do with the difference in the pressures. Now we can reach back to the formula for manometers. At the pressure on one end is the atmospheric pressure that's static pressure, which A is at static atmospheric pressure, plus the density of the fluid times G times the difference in the height column there. And so really that's the pressure at B is equal to the pressure at A plus the density of the air, where the density, sorry, that's the density of the water, it's the density of the liquid. Does it say what the liquid is? I don't know that it matters. Incompressible fluid, I suppose. We'll say it's water. So the density of the fluid, that's the liquid there, not the air, times G times D. But we don't even need to put any numbers. The point is that since the pressure at B and the pressure at A are not the same, then therefore their D must have a value. So like if the pressure at B equals the pressure at A, then D has to equal 0, right? But we established that the pressure at B is greater than the pressure at A. So D, that difference is greater than 0. Whatever it is, I don't know, but it's greater than 0. So there's going to be a difference. That's what I'm talking about right here. This ding, 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 right here. That difference in the liquid column height. That's why, A says, why is there a difference? The levels of the liquid are at different heights. So that D is the difference in the height, and it's because the pressure is different in each tube. So this is 3 marks for A. You need to establish two, that there's a difference in pressure, having to do with the fact that the air speed stops at B. So at B, the velocity stops, it's stagnation pressure. And so since that's stagnation pressure and A is the static atmospheric pressure, that's going to cause a difference in pressure, rather that not just a difference, but that B is greater than A, or that A is less than B. So that's 2 points there. And then because of that pressure difference, you need to explain why that causes a difference in the height, which we did over here with this P equals P naught plus rho GD. So there's that. So in typical mark scheme fashion, they use some shorthands, and I'm not 100% following them. It also breaks across pages, but I can walk you through how this works. And so by Bernoulli, we have 1/2 rho v squared plus rho gz plus the pressure is a constant. So they're going to be, that's for A, both sides, A equals B. Now there's no difference in the height, so there's no z, so rho gz is out. So we have 1/2, let me zoom in on this a little bit more. 1/2 density of air times the speed of the air at A squared plus the pressure at A is 1/2 times the density of air times the speed at B squared plus the pressure at B. Now, the deal with the pitot tube is that we have stagnation pressure at B, so there's no velocity there. So 1/2 rho VB squared is 0 because VB is 0. Velocity at B is 0. Also, at A, we have the static atmospheric pressure, and so that pressure at A is atmospheric. And we have the pressure at B by, I have to figure out what principle that is, but the P equals P naught plus rho fluid GD for the manometer. I call that the manometer equation. But so the pressure at B is the pressure at A plus the density of the fluid, the liquid in the tube, times G times the difference in the height, which they gave us 6 centimeters. The pressure at A, of course, is atmospheric. So the atmospheric pressure is on both sides of the equation, so that cancels out. And so we wind up with 1/2 density of air times the speed of the air at A squared is equal to the density of the fluid in the tube times G times the difference in the height. If we isolate the velocity at A, we get square root of 2 times the density of the fluid in the tube times G times the difference in height divided by the density of air. The density of the fluid was given, the density of air was given, the difference in the height is given. Watch out for those units, of course. The difference in the height was given in centimeters, so we put 6 times 10 to the negative 2. Multiply all that up and take the square root, and you wind up with 29 meters per second, which agrees with the mark scheme. The rest of the mark scheme is actually all the way over here. And yes, indeed, we have 29 meters per second, so that matches. All right. So now we're on number 3. So number 3, it says a condition for a Bernoulli equation to apply. Bernoulli equation only applies for ideal fluids. Ideal fluids. Well, what characterizes an ideal fluid? They are steady laminar flow, they are incompressible, and they are not viscous. So one of those 3 things that makes an ideal fluid, that's the condition for Bernoulli to apply. All right. Then they give us gasoline, density of 720 kilograms per cubic meter, and it's flowing in a pipe with an elevated section 1.2 meters above the ground. Y is the speed of the gasoline at X, the same as that as Y. It says continuity equation. So let's remember, so since AV is a constant, that means the area at X times the velocity at X is equal to the area at Y times the velocity at Y. And so since X and Y have the same area, they're going to have the same speed. And then BII, when's the difference in pressure between X and Y? And even though the velocities are the same for X and Y, you're like, oh, the velocities are the same, the pressure is going to be the same. No, it's not. There's an elevation change, and that's part of the Bernoulli expression. So let's remember, and I'm going to move this over to where the mark scheme actually is, which is over here. All right, and then X starts on the ground, so there's no height, so there's no rho gz there. But the second portion at Y, it's elevated 1.2 meters above the ground. so we'll need to deal with that. Now, we've already established that the velocity at x is equal to the velocity at y, so 1/2, it's also the density, of course, is the same as well, so the 1/2 rho v squared portions, they'll drop out. We wind up with the pressure at x, because the 1/2 rho v squared dropped out. The first rho gz for x dropped out because it had no height. And so we're just left with the pressure at x is rho gz plus the pressure at y, and we know the density is 720 kilograms per cubic meter. We have 9.81 for g. The height of the second pipe at y is 1.2, so when you multiply all of those up, we get the difference. I'm sorry, I missed the part where I subtracted py. I want the difference. He said it asks for the difference in the pressures, so it's px minus py is 8,500 or 8,500 pascals. And then we have BII says diameter at y is made smaller than at x. Why is there going to be an increase in the pressure difference? Well, there's going to be a difference in the speed, again, because that's the continuity equation. AV is equal to a constant. So the area of x times the speed of x is equal to the area of y times the speed of y. And it says you're reducing the diameter at y, so you have a decrease in the area. We're going to have an increase in the speed. So the v at y will be increased. And so if we go back to Bernoulli, now the velocities are not equal to each other, and we have an increase in the y velocity, which also keep in mind that the y velocity is squared, so any increase in the y velocity is going to be significant relative to the x velocity at the beginning of the pipe. And if that's an increase in the y velocity, then that means this portion is going to increase. That portion plus the rho gz is going to increase. And nothing has happened to the velocity at x or the pressure at x. That has stayed the same, but in order for these two expressions to be equal to each other, if the left side of the expression is the same and this portion of the equation is increasing, that means that the pressure at y is going to have to decrease as a result. And so it says the fluid speed at y will be greater because of the continuity equation. And then as a result, what I just said using Bernoulli, that means that the pressure at y is going to decrease. Okay, number 4. So 4 is talking about this sphere that is released into a fluid, and it says draw and label the forces acting on the sphere. And so we have the mark scheme kind of does that pretty well. Now, one thing that I want you to notice, they say the instant the sphere is released, and so that instant it's released, it's not moving. Of course, it starts to accelerate, but the instant it's released, it's not moving. So since there's no velocity, there's no drag force, you have to be moving to have a drag force. So there is weight pulling down, there's the buoyant force going back up, and but notice it says give no points if you include a third force, so be careful there. And also notice that it says do not accept just gravity. I hear physics students say that a lot. They say gravity, force due to gravity. Just saying gravity is not a force. You could have acceleration due to gravity. You could have force due to gravity. Gravity causes a force, but you can't just say gravity. That's more of a phenomenon. So you have to say weight or force due to gravity. Also notice it doesn't say anything for the point values, but the weight should be greater than the buoyant force. And the reason why that's true is because if the buoyant force and the weight were equal, which it could happen if something were floating, then the sphere would not fall. Does it say that it falls? It begins to fall. So since it begins to fall in the fluid, that means that the downward force needs to be greater. I maybe would have given this 2 marks, and I would have included that fact, but they made it 1 mark, and so I guess it doesn't matter if you drew the forces the same length. That would be wrong, but it doesn't say to take away points. All right, let's move on. And then B says, explain why the sphere will reach a terminal speed. So there is a drag force, and then the drag force is given by 6 pi times the density times the radius of the sphere times the speed of the sphere. And so since the force is greater, gravitational force is greater than the buoyant force, there is a net downward force, so the sphere accelerates. And again, just to reiterate why we know that the gravitational force is greater than the buoyant force, again, we come back to begins to fall. So since it begins to fall, we know that the gravitational force is not equal to the buoyant force. In fact, the gravitational force pulling down must be greater than the buoyant force in order for the sphere to fall. If gravitational force were equal to the buoyant force, then the sphere would float, or at least kind of like have neutral buoyancy and just kind of like maybe just bob around or something. But if it weren't disturbed, it would just kind of float. But the gravitational force is greater than the buoyant force, so there is a downward net force. And so we have net downward force. And of course, the buoyant force is not dependent on the speed, so the buoyant force stays constant. The buoyant force, of course, FB, or just B if you're following the data booklet, is the density of the fluid times the volume of the fluid displaced by the object times G. So that has no dependence on speed. And so as the sphere accelerates going downward, then the buoyant force is constant. But as the sphere accelerates, therefore the drag force is going to increase because the speed is increasing. Now that drag force will continue to get bigger until the net force is 0 and there's no more acceleration. And if there's no more acceleration, you get no more increase in speed, and so the drag force can't increase anymore. And so the drag force stops increasing when you hit net force equals 0. Now, what is that condition? And so when the sum of the buoyant force, which is constant, and the drag force, which is increasing up to the point that the net force equals 0, then the sum of those guys is equal to the weight. Then the net force is 0. We're no longer accelerating, and then we are falling at a constant velocity. And then we call this velocity value that we've now hit the terminal velocity. Now, the question says, explain why the sphere will reach a terminal speed. So probably if you get into that notion about the net force, like for instance, it says, as the ball falls, there is a drag force, right? When drag force plus the buoyant force is equal to the weight, then the net force is 0, right? And it says, or when the net force is equal to 0, which is what I just said, terminal speed occurs, or words to that effect. Terminal speed is mentioned in the question, so no additional marks for reference to it. Okay, I feel like it's hard to answer that question without talking about terminal speed, but they just say, don't just say a sphere reaches a terminal speed because it reaches a terminal speed. You gotta explain why, right? So there you go. That's B. Is there a C? There is a C. Yeah, C actually uses the derivation we just did. The drag plus the buoyant force equals the weight, gives some numbers, and it says calculate the viscosity of the fluid. Just noting here for my derivation for mg, I'm putting in the weight that was given of the sphere. I'm not using the mass because they didn't give me the mass, they gave me the weight. So mg, I'm putting in the weight, the 6.13 millinewtons that they gave me. Okay, numerator, I have mg. I put in the density of the fluid that they gave me. I put in the 4/3 pi. I have the radius, the 5 times 10 to the negative 3 meters. I'm cubing that times 9.81. And then in the denominator, I put in 6 pi, the radius. I probably could have canceled the radius in the denominator, and I could have put r squared in the numerator. Anyway, and I put in a terminal velocity. So we should get 0.0680 Pascal seconds. Let's see what we get. And I just realized that you can't do the r. You can't cancel the r and the r cubed because there's no r in the mg expression. So we'll just leave it as it is. Okie doke. And so after we plug in our numbers, we do in fact find that the viscosity. Yes, viscosity. I thought I was solving for density for a second. I'm like, that's not the density symbol. Viscosity is 0.0680 Pascal seconds. And here we are at number 5 of, I think, 9. So we have an ice cube floating in water. So with number 5, we have our ice cube floating in water. And so the ice cube then melts. What happens to the level of the water in the tube? And Mark's scheme says either you can talk about it from a weight perspective, kind of like Archimedes' principle, that ice displaces its own weight of water. Or you could say that the melted ice volume equals the original volume displaced, which makes sense. And so if it's the same volume and the ice melts, so then no change is going to take place. Now, if you take a look at that, though, you'd be like, now, wait a minute. That ice cube, it's kind of like maybe if the ice cube were just like this much, it's kind of like, oh, the water level wouldn't change if the ice cube were just this size right here. But you can be like, well, the ice is also this up here, so isn't that actually going to increase the water level? But don't forget, I need to get a better eraser here. Why is it not erasing that mark? So yeah, anyway, but don't forget that ice expands when it freezes. So yeah, that ice cube actually, when it melts, the ice cube will represent less volume of water than the total cube itself in the water and above the water. So that means that there's not actually the actual volume of water that's in that cube shown in the diagram, is just the amount here. So yeah, it's not going to change the water level. I'm not really sure why they broke the questions like this. But it says horizontal pipe is inserted to the cylinder so that the center is at a depth of 5 meters from the surface of the water. Diameter of the pipe is half of that of the tube. And so that's the pipe that they're talking about. So the pipe is D, the tube is 2D, and the center of the pipe that they installed is 5 meters from the top of the tube. And it says pipe is opened, the water exits the pipe at speed u, and the surface of the water moves downward with speed v. And say y is u, the speed that the water moves outwards. So yeah, let's kind of label that in. We have a downward water level speed of v, and we have an outward water speed of u, and it says y is u, the speed of the water coming out of the pipe, 4 times v, the speed that the water level is dropping. And yeah, it says continuity equation, so yes, that kind of makes sense to me, assuming that we're dealing with an ideal fluid. So AV equals a constant. And so we're dealing with area. They made reference to diameter. They say the diameter up at the top is 2 times the diameter of the pipe. And assuming that the pipe is a round pipe, we have A is pi r squared. Even if it were a square pipe, it would still be 4 times as much. So yeah, pi r squared, we have 2 times the radius. So up here we would have 4 times the area, and then down at this pipe is just regular area. So yeah, following continuity equation, if the top of the pipe has an area of 4 because has twice the radius, then the pipe would have an area of just A area. 4 times the area means that the flow out of the pipe is going to be 4 times as fast. And so there you go. So yeah, U is equal to 4V. And then it says the density of the water is 1,000 kilograms per cubic meter. And so it says calculate what that speed actually is. And so if we're looking at speed, that's going to be Bernoulli. And so we're going to set the Bernoulli is constant, the 1/2 rho v squared plus rho gh plus the atmospheric pressure is going to be the same both before and after. It's constant. So we have on this part here, this is the top of the pipe. And then down here, this is the outflow pipe, outflow. And if we're saying that the outflow pipe has a height of 0, then our rho gh there is going to be 0. And I don't love the way the IB does math, so I want to redo this. The atmospheric pressure is on both sides of the equation, so we cancel that out. Of course, the atmospheric pressure is on both sides because both sides are open to the atmosphere, both the top of the pipe and the outflow. But since they're on both sides of the expression, we can cancel it out. But yeah, the math checks out. It's funny that they gave the density of the water. The density is drops out of the expression. So you can see right around there, you can cancel out the density. So you didn't actually need the density to solve the problem, but we still end up with 10.2 meters per second for U, this outflow speed from the pipe. It says you can also solve by conservation of energy. Just making sure that I'm in the right spot, and here we are with number 6. But I wanted to stop this video at 30 minutes. It's now 36 minutes. Again, I think there are, let me track this back, 8. I thought there were 9 questions. Maybe there are only 8 questions, but it doesn't matter. We're pushing up on 40 minutes, so I'm going to cut this off here with 1 through 5, and then in the next video, we'll do 6, 7, and 8. Thanks.